Hello guys, welcome back to my channel, Memo African Motives. Still working on engineering science and 3, working on question papers and revisions. So actually in this platform we've got questions which is when on HIT, which is a continuation from the other classes that we've been working on question papers again. So in this platform we are given a question which is on question number 5, and as we can cross-check this, all the question is actually having 15 marks. So we shall focus on this question. So guys, if you are new to my channel and you want to be part of this family, you can consider subscribing so that you won't miss any of the classes that we shall be having from Memo African Motives. Okay, so the first question on 5.1 is to state 2 applications of STEAM. So that is the question. We need a condition where we are going to apply STEAM, which are the factors that we are going to use there. Okay, so this is what I'm having guys for you for the applications of STEAM. These are the best answers that you can actually have. Okay, so applications of STEAM on 5.1, these are the applications that you're going to have. So STEAM actually acts as a power source for locomotives, ships and hoist, and also we know that steam can be used to generate electricity, can be used to heat buildings, can be used to cook canned food in factories. Okay, so we've got medical equipment, cans and bottles are sterilized with steam. So as you can see guys, that steam actually plays a lot of roles. So there are so many roles, but these are the basic ones that they can like have, the ones that you can actually have according to the courses that you are doing. These are the best ones that you can actually have there. Okay, so now on 5.2 we are given a rectangular brass sheet. It has the following dimensions at 10 degrees Celsius. Okay, so I want you to take note guys, as indicated on the diagram in fig 3. All right, the coefficient of linear expansion is 20 times 10 to the exponent of, that's a -6 there per degree Celsius. The sheet temperature is then raised to 120 degrees Celsius. Okay, what actually happened here? This is what we want to see. This is a rectangular sheet that we are given, and we are given conditions when it is at 10 degrees Celsius, which means that is our initial temperature, the one that we are given here. That is our initial temperature, which is T1 of 10 degrees Celsius, and it's a brass sheet. So this is brass, and actually here we are just writing, but already we are given the coefficient of linear expansion. So that's the advantage that we're given. Okay, so what do we have? We've got the coefficient of linear expansion, which is actually this. This is your coefficient of linear expansion, which is 20 times 10 to the exponent of -6 per degree Celsius. Okay, so this is what we have. Then the temperature, the sheet temperature is then raised to, which means after some time, that's when we had that temperature. So that's your T2, your final temperature, which is T2, which is 120 degrees Celsius. Okay, so these are actually, that's your rectangular, the brass sheet. Like as you can see, it's a solid shape, that one, but what we just need is like a cross section of the diagram there. So this is just like a cross sectional area that we are talking about here. So the cross sectional area, you've got the length and the width, which is the breadth. So this is your breadth and this is your length. So this length is the original length, this breadth is the original breadth. So this is the original breadth, this is the original length. All right, so since this is a rectangle, we know that these are the same. So if this is 450 millimeters in meters, we know that you're going to use our units in meters when there is a condition that you have to use them in meters. Okay, so using in meters, this is going to give us 0.45 if you divide properly, that's in meters, and 350 divided by 1000, that's 0.35. So this is going to be 0.35 meters, which is the original breadth, the original length of the rectangular sheet. Okay, so let's quickly rush through to answer the questions now. Determine the following: the area coefficient of expansion. Okay, since we know we've got the linear the coefficient of linear expansion, then we've got the area coefficient of expansion. Okay, so the area coefficient of expansion is the one which is given as beta. Okay, this is the one which is given as a beta like this, which is equal to 2 alpha. Okay, so the area coefficient is 2 alpha. If it is the volume is equal to 3 alpha. Okay, so if this is 2 alpha, which is the linear coefficient, you're going to multiply 2 times our alpha here, which is this part that we had. This is your alpha, which is the linear coefficient of expansion, which is 20 times 10 to the exponent of -6 per degree Celsius. All right, so you just multiply these two numbers, 2 and 20 there, that's a 40 times 10 to the power -6 per degree Celsius. So that's what you're going to have there. You just leave your answer like that. Okay, it's best to leave your answer like that. Then the other question now is on 5.22. Take note, guys. The question is determine the following: the increase in area in square meters. These are millimeters, so we need meters, not millimeters, at 120 degrees Celsius, which means after an increase of temperature, what was going to be the area, what was the increase in area, what was the change in area, because the change in area, it can be a decrease or it can be an increase in area, but it's supposed to be in square meters. Okay, so let's start by finding the original area of the block that we are given. Okay, so this is what we're going to do, guys. This is what you're going to do from this information, this diagram here. Remember, you have got the original length and the original breadth of the rectangular sheet. So you're going to find the original area from these dimensions, which is the area at 10 degrees Celsius when it was initially at 10 degrees Celsius. What was the original area? And we know that the area of a rectangle is length times breadth. So it's going to be the original length times the original breadth. All right, so what is our original length in meters? Our original length in meters is 0.45. So that's 0.45 times the original breadth, which is 0.35. This is your original breadth, which is 0.35. All right, so you're going to obtain the original area from this part. So if you are to multiply, guys, this properly, you're going to obtain an area of 0.1575 square meters. So this is the original area, not the increase. The question, guys, we must answer the question. The question is determine the following: the increase in area. Okay, after 120. So why are we going to have the increase in area? So we can use the formula for the increase in area in this case, which states that we talked about this, but I wanted you to see also from the formula sheet. But let me just write it down. So the increase, which is the change in area, is equivalent to, you can write it as 2 alpha, or you can use alpha inside the question. So you can, like, it was supposed to be like this: original area times 2 alpha like this, times the change in temperature like this. So that's why I'm saying you can start with this 2, it's fine. So you can write it as 2 times the original area times alpha times the change in what? In temperature like this. So it's still one and the same thing, or you can write it like this. As long these are multiplying to each other, you're going to obtain this change in area, which was the increase in area. So the change in area is going to be 2 times the original area of the rectangular block when it was at 10 degrees Celsius, which is this original area, the one that we calculated from the block, which is 0.1575, times the linear coefficient of expansion. Okay, so take note, the linear coefficient of expansion is this one that we have, 20 times 10 to the exponent of -6. So you've got 20 times 10 to the power -6 times the change in temperature. So remember that the change in temperature means T2 minus T1. Okay, so this is your T2, 120 minus your T1, which is 10. So 120 minus 10, which is 110 degrees Celsius. So this is our change in temperature, which is 110. So we are going to multiply by the change in temperature, which is this change in temperature, which is 110. Okay, or you can just use it as 120 minus 10. It's still one and the same thing. There's no change there, guys. Okay, so using your calculator, you're going to multiply everything there. Your calculator is going to give you something like this if you round off properly. 6,93 times 10 to the power minus 4, which is in square meters. So this was the change in area, which is 6,93 times 10 to the power minus 4. So the idea there is that yeah, actually I forgot to have my calculator, but that is the idea there. Okay, so I want you to see something. When you are given this, some might confuse to say in the formula sheet, this is what I'm given. Okay, this is what you have in your formula sheet. Okay, change in area is the original area times beta times change. It still is one and the same thing. This beta here is the one that you actually calculated before. Remember, we said our beta here is 40. So you can use this in place of this part, because as we said, 2 times alpha. So this is your beta, this 2. So that's why I wrote it like this. So if you use beta, you don't use 2 beta again. No. If you use this alpha here, the linear coefficient, that's when you multiply by 2. So take note, guys. You could have used another formula. Still, it's one and the same thing. All right. Then we have got another question now, which is a continuation from this part, which is the dimensions now, that is on 5.23, the dimensions at 120 degrees Celsius. Which dimensions are they talking about? Okay, this is what we had, guys, from the diagram. I hope my diagram is still there. Okay, this was my diagram here. Okay, this rectangle, that a rectangular shape that I showed you here, it's a rectangle which was taken from the original length and breadth of the brass, which was at 10 degrees Celsius. This was the rectangle. So these are the dimensions. The dimensions, we are simply referring to the sides. That's the dimension. So which means we are talking about the length. So the original length is 0.45. This is your original length. The original breadth is 0.35. So what is going to be the length after, which is at 120 degrees Celsius? Yeah, this is what the question is saying. What is going to be the dimensions? What is going to be the length? What is going to be the breadth after or at 120 degrees Celsius? What are we going to have there as our new dimensions? Okay, so this is what we are going to do. We know that the new dimension, which is maybe its length, is equivalent to the original length plus the change in length. This is the new dimensions. That is the dimensions at what? At 120 degrees. The same thing is with the breadth. The new breadth is going to be the original breadth, which was the breadth at 10 degrees, plus the change in the breadth, which is the change in the breadth of the given the rectangle there. So if this is the formula, the original length is already there, but we need to find the change in length, the change in the breadth. So there's no way we are going to use this formula. So this, I'm going to keep it aside. All right, so we are going to find first the change in length, because we need this in our formula, and we know that our formula for change in length is the original length times 2 times alpha. This time it's just alpha times the change in temperature. I think I showed you the formula there. So this is the change in length, which means the length at what, at 120 degrees Celsius. Okay, so I wanted you to see this so that you don't confuse when you are in exam. You don't confuse between these formulas. So this is the change in length, original length, linear coefficient, then the change in temperature, or then the final length. This is the formula now, like I was saying, that you're going to add the original length and the change. Okay, so that's what what the question is saying there. All right, so this is the change in length, which is our original length. So we are back to our diagram here. This was our original length here. The length, this is 0.45. So 0.45 times the linear coefficient of expansion, which is 20 times 10 to the power negative 6. So we've got 20 times 10, the exponent of negative 6, times the change in temperature. The change in temperature, we say it is 110 degrees. So this is 110. All right, so you're going to multiply this from your calculator. This one is just going to give you a direct something like 9.9 times 10 to the power minus 4. Times 10 to the power minus 4, like this. Okay, so take note, I used the 0.45, which was in meters. So this change in length is also in meters. So the question, guys, is not to find this change in length. No, this is not the question. This is the change in length. The question is to find the dimensions, guys. Okay, let me take you back here. This is the question. Determine the following, the dimensions at 120, which means we need the new length. Okay, so the new length, from what I said here, this is going to be our new length, or the final length, which we said is going to be the original length plus the change in what, in length. Okay, so this is going to be original length plus the change in length. So our original length is the one that we had before. The original length was 0.45. So 0.45 plus the change in length, this one that we obtained here, 9.9 times 10 to the power minus 4. This is your change in length. Okay, so combining these two numbers, so this is actually in a bracket like this. You can just put it in a bracket so that you know that it's one thing, that one. Okay, so this is what you're going to obtain. It's going to be a decimal, like 0.45099. all right, meters. So this is now your final, you can just write as LF to represent the final length. So this is now the final length, which is the length at what? The length at 120 degrees Celsius. But this is not only about the length. The question is dimensions. So dimensions, we're talking about length, we're talking about width. So it means we're going to do the same thing for the breadth of the rectangle, because as we saw that from our diagram, if I'm still having this diagram with me, okay, there. This is what we had from our diagram. There are two things here. We've got the length and the breadth. So these are the dimensions that we are talking about. So the breadth is going to have its final dimension. So that is what we are going to do, just like what we did for length. So we are going to find the change in breadth first, which is the original breadth times alpha times the change in t. So this alpha is the linear coefficient of expansion. So the original breadth, this is our original breadth. We are now here 0.35. So you've got 0.35 times the linear expansion, which is 20 times 10 to the power minus 6. 20 times 10 to the power minus 6 times the change in temperature. This is our change in temperature, which is 110. So you're going to have 110 as a change in temperature. Okay, so also just like the other one, this is what I actually got. It was 7.7. Yeah, 7.7 times 10 to the power minus 4. This was in meters, so this change in breadth is going to be in meters. Okay, but I want to find the final breadth, which is the final dimensions for the breadth. So it's going to be the original breadth, which is the one that I had, plus the change in the breadth. All right, so this is the new dimension now. What is our original breadth? Original breadth is 0.35, or you can take it from the diagram, 0.35 plus the change in the breadth, which is, this is your change in breadth, which is 7.7 times 10 to the exponent of -4, which is a one or single term like that. Okay, so you can just combine this from your calculator, which is going to give you something like 0.35077, which is in meters. So this will be your final breadth, or just B like that is fine, because we know that we are talking about the dimensions, the new dimensions. So you can just write as we have to F, that F is representing final breadth, the final breadth, the final length, the final whatever that you're talking about, that is that F is representing. So like I said, you can write this in any way that is best for you. All right, now let's see this one on 5.3, an interesting question actually that we had there. So but it takes a lot to reach this question. I don't know how are we going to understand it. Looks simpler, but there are so many things that was included there. Okay, the question is calculate the volume of water in liters. Okay, so that's the first thing. We need volume of water in liters, required to cool 45 steel sheets. Take note, guys, we've got 45 steel sheets. Shafts, sorry, these are steel shafts. All right, the initial temperature of the shaft is 800 degrees Celsius, and that of water is 35 degrees Celsius. The mass of each steel shaft is 300 grams. Take note, the mass of each steel shaft is 300 millimeters. So these are things that you're supposed to take note, guys. We need the volume of water. Okay, let me change. We need the volume of water in liters. This is what we need in liters. We are talking about 45 steel sheets, right? Then the mass of each, these are the key words, guys, each steel, okay, is 300 grams. The final temperature of water and steel is 110 degrees. The final temperature of water and steel combined together, that's the final temperature, that one. All right, so we've been talking about these typical questions, but this one is very, very important. It's deep. It's actually having some things that we didn't actually mention from previous classes, which I want you to understand from this question. Okay, this is what we have. We still have the same thing. Okay, we need our volume in liters. Okay, we shall talk about this later on, but we are required to cool 45 steel shafts. Okay, so we've got steel in this case, and we have got water here. Okay, so these are 45 steel shafts that we are talking about. They are 45 in number, all of them. Okay, then what happened? The initial temperature of the shafts, which shafts are we talking about? These steel shafts, it's 800 degrees Celsius. So this is the temperature of the steel shaft. That is the original temperature. So this is the original temperature of the steel shaft. Like I use, guys, I always use S to represent the temperature of something, temperature of steel. So it's S. So that's why I do this. Pardon the way I write. Maybe you are not familiar to it, but that's what I'm used to. And that of water is 35 degrees Celsius. That of water, so we've got the temperature of water, so it's T water, which is at 35 degrees Celsius. So this is the temperature of water. All right, then let's move on. There's something that is important here. The mass of each steel is 300 grams. The mass of each is 400. And how many do we have? We have got 45 of them. So what is going to be our total mass? This is the question. Okay, so this is what you're going to do. Each steel shift has got 300 grams. So you're going to convert first grams to kgs. Okay, we know that to convert grams to kgs, you divide by 1,000, which is going to give you 0.3 kgs. So each steel shift has got 0.3 kgs, and there are 45 of them. So which means our mass is going to be the mass of each steel shift times how many of them. They are 45 in number, so you multiply by 45 steel shafts that we are given. So I don't know where I'm giving this shift, guys. Steel shaft. All right, so if you multiply properly 0.3 times 45, you're going to obtain something like 13.5, which is actually in kgs, because we converted this to kgs. So that is the mass there. So which means the mass of the steel shaft here is 18.5 kgs. Okay, so how you see how tricky this question was, guys. This is a tricky question, and you're supposed to be very, very careful with these typical questions. Okay, then I think that's the only thing that you're given, and you're given that the final temperature of water and steel shafts is 100 degrees Celsius. So this is the T2, the temperature of the whole system when combined together. So this is T2, which is for everything. So your T2 for the system is 100 degrees Celsius, the temperature of the whole system. But as we know that when we are working with steel, we are working with water, there is a need for us to know their specific heat capacities. So we need to know the specific. Some they write this as this specific heat capacity. It's still one and the same thing, guys. Do not confuse with me. I just write like this. Okay, the specific heat capacity of steel. Okay, so we need the specific heat capacity of steel. This is the specific heat capacity of steel here. Specific heat capacity of steel, which is 500. I hope it's clear, or let me do this. Okay, that's a 500 joule per kg degree Celsius. So you got 500 joule per kg degree Celsius. Okay, then we need also of water. And of water here, we just take it at once, which is 4187. So you've got 4187 joule per kg degree Celsius, like that. Okay, so this is what we have. Then the question, remember, the question is to calculate the volume, guys. We need to calculate the volume. Okay, where am I going to have volume, guys? Because here I don't have anything that has to do with the volume. Okay, this is what I'm going to do. I know that there is a relationship between the heat that is lost and the heat that is gained here. We need the volume in liters, remember. So we are going to use that relationship. I want you to see what is going to happen here. The heat that is lost is equivalent to heat that is gained. I know we are now used to this formula because we've talked about this from a lot of questions, question papers actually. So remember, I told you that the part that is lost, that lost its heat, is the one that is decreasing in temperature. The steel started with 800 degrees Celsius, and now it's at 100, because this is the final temperature of the system. So as you can see, it has decreased. So there is a loss here. Okay, and this temperature of water started at 35, and at the end it's now at 100. So as you can see, there is an increase, which means this one, there is a gain. So here it gained from 35, it increased to 100, because this is the final temperature of the system for water and steel at the same time. So water increased while the steam lost. So the heat lost is from the steel, the heat gained is for the water. Okay, so this is Q, steam, which you know that is MC TS minus T2, since there is a lost here. So this is mass of steel, mass specific heat capacity of steel, temperature of steel, temperature of the final system, which is for water and steam. The one that is gained, so we say this is for steel and this is for water. The water is the one that is gained, and the heat for water, it's mass of water. Okay, specific heat capacity of water, but this time it's going to be T2 minus. So it's now T2, because T2 it's greater than what? It's greater than this one because it has gained. So it's T2 minus T water, the temperature of water. Okay, so what we are going to do is to actually determine, substitute the values and determine the mass of water, because we've got the mass of steel. Remember, the mass of steel we are given 13, 13.5 kgs. Okay, so you're going to have 13.5 times specific heat capacity of steel, which is 500, times the change, which is TS minus, which is 800 minus 100. So we've got 800 minus 100, which is equal to mass of water. We do not have this mass of water, times the specific heat capacity of water, which is 4187, into, or times T2 minus T water, T2, which is 100, minus the temperature of water, which is 35. So it's 100 minus 35, like this. All right, so you are going to actually combine. You can just combine these numbers, guys. This part here, if you multiply, because this is 13.5 times 500 times 800 minus 100 in a bracket like that, you're going to obtain something like 472,500 like this, which is equal to, we do not have this mass of water, but we can simplify these two numbers, these numbers here. So you're going to obtain 272,155 there, times this mass of water, times the mass of water. So to find the mass of water, definitely I'm going to divide by this. I'm going to divide by this number both sides. So it means the mass of water is going to give us something like 17,3614300, something like that. All right, so this is the mass of water, but this mass of water, guys, is in kgs. Okay, if you round off, we can obtain 17,361, but this 4 cannot change, so it can be 361. Okay, but this mass of water is in kgs, but the question is, we need to find the volume of water. Calculate the volume of water in liters required to cool. So we need the volume of water in liters, not in kgs. So what are we going to do there? How are we going to convert? Okay, so relationship is simpler. You're going to use the relationship of a kg to be equal to 1 liter. So that is the idea, that you're going to use a kg to be equated to 1 liter. So if a kg is equal to 1 liter, what does it mean? It means this is going to be 17,361 in liters. This is 1:1, like when this is 1, this is 1, when this is 2, this is 2, when this is 3, this is 3, 1:1. So when this is 17,361, this one is just going to remain as 17,361, because they are equal throughout. But this is now in liters, because you're asked to give that volume in liters, not in kgs. So answer the questions, guys. It's very, very important that you understand what the question is saying. So as you can see, that's how they can actually ask these questions on it. These are difficult, not difficult actually, but these are straining. You just need to at least revise a lot, so that you actually understand the question, how does it ask, and how do you answer the question. Also in assistance with your formula sheet. Remember, you'll be having your formula sheet, so it can also assist you. It's also important for you to understand or to analyze your formula sheet properly. Okay, so that's it, guys, for Mason African Motives, working on engineering science N3 past exam papers. Till we meet again.